Today we are looking at an introduction to the periodic table, your guide to the elements. Our mission today is pretty straightforward. Get you, the early chemistry student, up to speed on this really fundamental chart. We're not just talking about what it is, but, how it got built and why its structure is just so incredibly powerful for predicting things in science.
Absolutely. It's so much more than just a poster you see in classrooms. You really need to think of it as, well, nature's ultimate filing system. I mean,
Oh,
think about organizing anything huge, like a library with, what, hundreds of thousands of books?
right. You need something like the Dewey Decimal System just to find, say, a specific biography without spending days searching. It'd be chaos otherwise.
Exactly. And chemistry started out in that kind of chaos. Imagine getting all the basic building blocks of everything, over 100 different elements, and someone just says, okay, make sense of this.
Yeah, it's like walking into a massive grocery store where the milk is next to the power tools and the bread is somewhere in the frozen food aisle. Good luck making dinner.
That's a great analogy. That's precisely the jumble early chemists were dealing with. The periodic table brings this immediate, almost elegant order. It lets us find things, sure, but more importantly, it reveals the hidden relationships between elements.
Okay, so let's trace that journey from chaos to order. Back in the early 1700s, there weren't that many known elements, right? Just a few.
Yeah, maybe a dozen or so that were well established, like copper, gold, lead, things known since antiquity.
Mm.
But then, as measurement techniques got better, boom, new elements started popping up much faster.
And that created the pressure to organize them somehow.
Precisely. The first, let's say, significant attempt came from Johann Dobereiner, a German chemist around 1829. He noticed some elements seemed to come in threes.
Threes, like what?
Well, he'd find a set, like lithium, sodium, and potassium, that had really similar chemical and physical properties. He called them triads.
Okay, similar properties grouped in threes. What was special about them?
Here's the neat part. He found a mathematical link. If you took the atomic mass of lithium and potassium, the first and third elements, and averaged them.
You get something close to sodium's mass, the middle one.
Exactly. Sodium's mass, about 22.99 AMU, that's atomic mass units, was pretty much the average of the other two. It suggested some underlying order.
But it didn't work for everything.
Nope, that was the problem. It was a cool pattern, but you couldn't fit all the known elements into these neat little triads. So, clever idea, but it just wasn't universal. It fell short.
All right, so triad idea, interesting but limited. Who tried next?
Next up, about 35 years later, 1864, you have John Newlands. He took a different approach. He just lined up the known elements by increasing atomic mass. Simple enough.
And what did he find?
He noticed something. Periodic. Like every eighth element seemed to echo the properties of the first one in that sequence. Kind of like notes on a musical scale repeating every octave.
So he called it the law of octaves. Makes sense.
Uh,
Was that the breakthrough?
Well, not quite. It was a huge step conceptually looking for that repeating pattern, that periodicity. But the scientific community wasn't buying it at all
Ah.
because his law basically stopped working for elements heavier than calcium. After that, the pattern just broke down completely. So his work got ignored, even ridiculed pretty harshly.
Ouch. I read they were really dismissive, like asking if he'd tried arranging them alphabetically next.
Yeah, something like that.
Yeah.
It really shows how resistant people were to the idea that organization could be based on predicting unknown connections, not just listing known facts by weight. The key thing with both Dobereiner and Newlands is they were focused on properties and, crucially, atomic mass.
Okay, so mass isn't quite the right organizing principle. That sets the stage for the big one, right? Dmitry Mendeleev in 1869.
Exactly. Mendeleev, he was actually writing a chemistry textbook, trying to explain the elements to his students, and he used this fantastic, almost low-tech method.
The flashcards, I remember reading about this.
Yes. He wrote down each of the 63 known elements on a separate card, its name, atomic mass, key properties. Then he just started shuffling them, arranging them, like playing solitaire, until patterns emerged.
And the pattern he saw was periodicity.
That was the core insight. When he arranged them by increasing atomic mass, he saw that similar chemical behaviors popped up again and again at regular intervals, like a pendulum swinging back and forth.
But wasn't there that issue with tellurium and iodine, where just following the mass didn't quite work?
Ah, yes. The famous Ti anomaly. That's where Mendeleev's genius really shines. Tellurium, T, actually has a slightly higher atomic mass than iodine, if he stuck strictly to the rule of increasing mass.
Iodine should come first, but he flipped them. Wait, he broke his own rule.
He did, and that's the brilliant part. He looked at iodine's properties: highly reactive, clearly a nonmetal, very similar to fluorine, chlorine, bromine further up the column. Tellurium's properties just didn't fit there.
So he trusted the chemical behavior over the measured mass?
Precisely. He basically said the mass measurement must be slightly off because chemically, iodine belongs here. He prioritized the periodic pattern of properties.
Okay, that's bold. But the really famous part is the gaps, right? The predictions.
Absolutely. He didn't just arrange what was known. He saw where elements should be but weren't discovered yet. He left empty spaces in his table.
And he didn't just leave them blank. He actually predicted the properties of the elements that would fill them.
Yes. He famously predicted an element he called Ica aluminum, meaning like aluminum, that should fit in a specific spot below aluminum. He described its expected atomic mass, density, even how it would react.
And then,
Just 4 years later, a French chemist discovered gallium. And guess what? Its properties were an almost spooky match for Mendeleev's Ica aluminum.
like how close?
Get this. Mendeleev predicted an atomic mass of about 68 MeO. Gallium's is 69.9. He predicted a density of 5.9 gC-mina. Gallium's is 5.94. It was remarkable validation.
Wow. Okay, that's why he gets the primary credit. Even though others were working on similar ideas, that predictive power was undeniable.
Exactly. It showed the table wasn't just a filing system. It was a predictive engine. That's why element 101, Mendelevium, is named in his honor.
But even Mendeleev's table wasn't perfect, right?
Yeah.
Because they didn't know about it.
Protons, or the nucleus, really. Remember, Mendeleev was working decades before Rutherford discovered the atomic nucleus in 1911. He was ordering by mass because that's what they could measure accurately.
So the final piece of the puzzle came later.
Yep, just a couple of years after the nucleus discovery. In 1913, a young English physicist, Henry Moseley, was doing experiments with X-rays.
Okay, what did X-rays have to do with it?
He was firing X-rays at different elements and measuring the wavelengths that came off. He found this incredibly consistent mathematical relationship between the X-ray wavelength and the element's atomic number.
An atomic number is the number of protons.
Exactly. The positive charge in the nucleus, which equals the number of protons. Moseley realized this was the fundamental property that defined an element, not its mass. He proposed that the table should be ordered by increasing atomic number.
And did that fix the tellurium iodine problem?
Perfectly. Tellurium's atomic number is 52. Iodine's is 53. Arranging them by atomic number puts T before I, exactly where Mendeleev had placed it based on properties, but now the fundamental rule also put it there. No more anomaly.
So that gives us the modern foundation.
Right. It leads directly to the modern periodic law. When elements are arranged in order of increasing atomic number, there's a periodic repetition of their chemical and physical properties. That's the bedrock principle.
Okay, law established. Now let's quickly navigate the actual table we use today, rows and columns.
Right. The horizontal rows are called periods. There are 7 of them. Think of them like floors in a building.
What do elements in the same period share?
They all have the same number of principal electron shells, or energy levels, that are occupied by electrons. When you start a new row, you're starting to fill a new main energy level.
And the periods get longer as you go down. Period 1 has only 2 elements, hydrogen and helium. Then 2 and 3 have 8 each.
Correct. Then periods 4 and 5 jump to 18 elements. And periods 6 and 7 have 32 each.
Why the big jump?
That's because you start filling inner electron subshells, the d block orbitals in periods 4 and 5, and then the f block orbitals in periods 6 and 7.
Right. Those 2 rows usually pulled out at the bottom, the lanthanides and actinides.
Exactly. They actually slot into period 6 and 7, but we pull them out just to keep the main table from being ridiculously wide. It's purely for visual convenience.
Okay, so curias are rows based on electron shells. What about the vertical columns?
Those are the groups, or sometimes called families. There are 18 numbered columns. And this is where the chemical similarity really shows up.
Elements in the same group act alike.
Yes, they have very similar chemical properties. And the reason is fundamental. They have the same number of electrons in their outermost shell.
The valence electrons.
Precisely. Take group 1, the alkali metals, lithium, sodium, potassium, etc. They all have just one valence electron. That single electron dictates their behavior. It makes them all super reactive, especially with water.
So the group number tells you something about the valence electrons, which tells you how it will react.
In many cases, yes, especially for the main group elements, groups 1, 2, and 13, 18. It's incredibly predictive.
And there are 2 ways to number the groups, right?
Yeah, you need to be aware of both. There's the older AB system, often used in the US, like 1A, 2A, then skipping the middle block to 3A through 8A. And then there's the simpler internationally recognized IUPAC system, just numbering them 1 through 18 straight across.
IUPAC, that's the International Union of Pure and Applied Chemistry, the official rule makers.
That's them. And speaking of official, they're the ones who confirmed the completion of the 7th period back in 2015.
Oh yeah, the newest elements.
Right. We now officially have nihonium, NH, element 113, named for Japan, moscovium, Mikie, 115 for Moscow, tennessine, Ts 117 for Tennessee, USA, and oganesson, Og 118, named after the physicist Yuri Oganesson, who's been a giant in discovering these heavy elements.
It's kind of mind-blowing that we're still making new elements, but these super heavy ones aren't exactly stable, are they?
Not at all. Pretty much everything beyond uranium, element 92, and certainly these newest ones, are synthetic, made in labs by smashing atoms together. And they're incredibly unstable, usually decaying in tiny fractions of a second.
Okay, so we have the structure, the law, the elements. Let's quickly classify them. Broad categories.
3 main types: metals, nonmetals, and metalloids. First, the metals. They dominate the table. About 80% of elements fall into this category. You find them mostly on the left side and in the middle.
And their properties are what we typically think of as metallic, right? Shiny, good conductors.
Exactly. Good conductors of heat and electricity. They usually have luster, shininess. They're malleable, meaning you can hammer them into sheets like aluminum foil. And they're ductile. You can draw them into wires, like copper.
Are they all solid?
Almost. All metals are solid at room temperature, except for one famous exception: mercury, Hg, which is a liquid. On the other extreme, you have tungsten, W, with the highest melting point of any metal, over 3,400 degrees C.
Okay, metals on the left and center. What about the right side?
Over on the upper right, you find the nonmetals. Property-wise, they're pretty much the opposite of metals.
So poor conductors, not shiny.
Generally, yes. Poor conductors of heat and electricity, they tend to be dull rather than lustrous. If they're solid, they're often brittle. They'll shatter rather than bend.
And they exist in different states at room temp.
They do. That's a key difference. You have nonmetal gases like nitrogen, oxygen, helium. You have one liquid nonmetal, bromine, Pr. And you have solid nonmetals like carbon C and sulfur.
Sulfur, used in rubber. And carbon, the basis of life.
Absolutely. Carbon's ability to form bonds is the foundation of organic chemistry. Helium's inertness makes it useful for balloons and cooling MRI magnets.
Okay, metals, nonmetals. What's in between?
Wedged between them, along a kind of diagonal stair-step line, are the metalloids, sometimes called semimetals.
Stair-step line. Is aluminum on that line?
Good question. Aluminum actually touches the line, but it's firmly classified as a metal due to its properties. The metalloids are elements like boron B, silicon Si, germanium G, arsenic As, antimony At, tellurium T.
And their properties are mixed.
Yeah, they show characteristics of both metals and nonmetals. The classic example is silicon Si. It has a metallic luster, it's shiny, but it's brittle, like a nonmetal.
And its conductivity.
That's the crucial part. Its electrical conductivity is intermediate, better than a nonmetal insulator, but not as good as a metal conductor. That makes it a semiconductor.
Which is why it's essential for computer chips.
Exactly. That property basically enables modern electronics. Other metalloids have uses too: boron in heat-resistant glass, arsenic historically in pesticides, though less now, antimony to harden lead for batteries.
Got it. Metals, nonmetals, metalloids. Simple classification, but based on real properties linked to their position.
Precisely. The table organizes them, and their position tells you what kind of element they are.
All right. We've gone from early confusion to Mendeleev's insights, Moseley's atomic number fix, and navigating the modern layout and categories.
It's quite a journey, showing how science builds on itself to arrive at this incredibly powerful tool.
And the real takeaway, the so what for you listening, is prediction. Right?
Absolutely. Knowing an element's position, especially its group, lets you make really good guesses about how it will behave chemically. You can anticipate reactions, understand properties, all based on those patterns. That's the true magic of the table.
So we know period 7 is now officially full, but those super heavy elements are fleeting, just existing for fractions of a second. It kind of leaves you wondering, will scientists ever manage to create a new heavy element that's actually stable enough to be more than just a scientific curiosity, maybe even useful someday?
That's the million-dollar question, isn't it? The island of stability is a theoretical prediction, but whether we can reach it and find something lasting, that's something for the future to maybe answer. Definitely something to think about.
Indeed. A huge thank you today to the geeky gamer science teacher for creating the awesome material that fueled this deep dive.